Welcome, everyone. Thank you all for being here. Tonight, we are joined by Professor of Physics and Astronomy at Columbia University, Janna Levin. She is Director of Sciences at Pioneer Works, a Guggenheim Fellow, and author of How the Universe Got Its Spots and Black Hole Blues. In this live stream event, Janna will take you on a tour inside a black hole and reveal how their mysteries contain answers to some of the most profound questions ever asked about the nature of the universe. Without further ado, it is my pleasure to welcome Janna Levin.
Thank you so much. Really appreciate people tuning in. It's strange to be doing this remotely, but that's the world we live in right now. I really want to talk to you today about black holes. And I know it's a subject that people think they already know everything about black holes. And I remember when I first started talking to a friend about the idea that I was going to write this book. He's a science writer, a very famous science writer who will remain nameless because he didn't want to appear foolish. But he said, "Don't I know everything about black holes?" And I asked him, "Do you know that they are nothing?" And he was kind of stumped and said, I guess I don't know anything about black holes. And that's kind of how this book was born that I'm going to be talking about today, which is Black Hole Survival Guide. It's really an attempt to kind of shuck away the veneer of previous impressions and give a new identity to black holes. And the black holes are really the hero of this very small little pocket guide. I wish I had a copy in front of me to show you, because we have some very beautiful covers in the UK. Now, I'm reminded when I set out to write this book of this great Mark Twain quote, which is, I didn't have time to write a short letter. Sorry, I just messed it up. I messed up my quote. I didn't have time to write a long letter, so I wrote a short one instead. And it's a great witticism because it really does take an investment to write a short book. And I really wanted to take the time to write something very short and dense and readable, like the black hole itself. It's just kind of consumable. And what I'd like to do for this next time together is imagine the exploration of a black hole. And this beautiful image, which was done by the artist Leah Halloran, she did a series of more than 20 unique paintings for the book. This beautiful image that Leah painted really represents a lot of what we're going to be talking about, which is a human exploration, an imagined, a fantasized, hypothetical human exploration of a black hole. Now, the first point I really want to make, which we're going to kind of get to, is that a black hole is actually nothing. And it is less of an object than it is a place. You should think of a black hole as a place in space-time. And we'll spend some time trying to get there. But if you were this astronaut falling across the event horizon, there's really nothing there. And that's a really profound concept from relativity. So let's begin in the beginning. One of the most important things to begin with is the concept that space-time is curved. The whole concept of a black hole emerges from Einstein's theory of gravity as a curved space-time. And it is an incredibly sophisticated theory mathematically. It's beautifully concise as well. But the intuition for why do we think of space-time as curved is not that hard to get to. And so I want to convince you that in a couple simple steps, we can get to the concept that black holes are curved. So imagine, or that space-time is curved and that black holes are a consequence of the curved space-time. So imagine you are in empty space, and imagine there are no markers. There's no Earth, no sun, no planetary systems, no galaxies. If you were floating in that empty space, we call that falling, even if you're not technically falling towards an object, we call that free fall. If you were freely floating, just another way to think about it, freely floating weightlessly in this expanse of empty space-time, and you were to throw a probe, and your probe helpfully illuminated its path, like in this painting, you would find that your probes traveled on straight lines. That is just what you would find. And if another observer floated past you, she would also imagine that, or observe that probes traveled on straight lines, even if you were moving relative to each other and you were floating in this empty space. And you would deduce, because of these straight lines, that space-time was flat. And what we really mean by flat is straight, that everything travels and falls freely along straight lines. Now, you can do this experiment in your home. I mean, maybe you're watching the news. I don't know. The news looks pretty bad in the UK. I lived in the UK for a long time, so it's close to my heart. But the news is pretty bad here in the US too. So suppose you're watching the news and you're on your couch and you decide to throw your remote at the news. Your remote does not travel in a straight line. You well know that your remote follows an arc in space. It will likely, maybe it'll hit the television, but if the television is far away, it will likely fall to the ground. And this very simple observation, which can be made around the globe from Earth covering couches, that free falling objects, once they are released and they're falling weightlessly in your room or in Australia or in Bangladesh or in New York, that they follow curved paths. And that intuition was really Einstein's greatest. He deduced, or he tried to mathematize the concept that what the Earth has done is curved the space-time around it. And that falling objects that are falling weightlessly in this empty space, because really the Earth is not technically touching that remote control that you've just thrown across your room, that it is what's actually happening is that remote control is falling freely along the curves in space. And so he had this profound intuition that what's really happening around the Earth is that there's this imprint in the shape of space-time from the mass and energy of the Earth, and that objects fall freely and weightlessly along the curves in space-time. And if you sat there mapping as you threw things faster, slower, drop them straight down, you would make a map of space-time that charted the curves in space-time. Now, this idea took Einstein a very long time to formalize. It was more mathematical in some sense than Einstein intuitively is. And he struggled with the mathematics. He wrote down several incorrect mathematical descriptions, but by 1916, he publishes this beautiful, concise, you can think of it as one mathematical expression from which we can deduce the entire theory of curved spacetime. Other people come along in his wake and begin to predict things like the Big Bang and even black holes. But to do that, it's not just space that's curved, which is a little bit easier intuitively to imagine. He also understands that time warps because of the Earth. And this is a real phenomenon. It's harder to visualize, it's harder to conceive of, but we actually use this in our phones. If you have a phone and you use a GPS system and you try to call a car to pick you up on a specific corner, or you try to use maps, or you drop a pin to a friend, all of those apps, in practical terms, require a correction for the fact that clocks nearer the Earth run more slowly than clocks further away, like in a low Earth satellite in a low Earth orbit. And if that correction isn't made, that time is warped by the presence of the Earth, then you will be completely unable to pinpoint your corner in your GPS unit. And so this is a real effect. Time is warped by mass and energy. The closer you are to the Earth, the slower your clocks run relative to somebody further away. But as we all experience, if we're on the Earth, we don't feel time running slowly. We're all synced up. My biological clock, the pace of my breaths, the way and rate at which flowers rot, all of those things are perfectly synced with my clock. So it's not as though I experience something different than somebody in a space station in low Earth orbit. But when we compare our experiences, we realize that we're out of sync, that our clocks are not keeping time. And it is a real effect. Time is not absolute. It runs differently depending on where you are in the universe and where you find yourself in the curved space-time. Now, it was quite a profound observation that Einstein made, that not only does matter and energy warp space and time for regular, ordinary material objects, it also does so for light. And that's a harder experiment to perform in your living room. If you shine a flashlight from your couch, the path that the light takes does not appear to be curved. It really looks straight, but it's not. And the reason the path of light, if I shine a flashlight, seems to hit the wall at eye level, exactly where I shot it, is simply because light is traveling so fast that the curves are more gradual and we don't notice. They appear to be straighter, and they are straighter than for a heavy object like a remote control, but they're not perfectly straight. Now, the first demonstration of this observationally came with Sir Arthur Eddington, who was not a sir at the time. Arthur Eddington is an English astronomer who was a pacifist and a Quaker, and did not enlist in the war effort during World War I. He was very much a generalist and a global thinker. And in 1919, he initiated an eclipse expedition. To be honest, he tried to do it earlier in the Soviet Union to disastrous effect several years earlier. But this is 1919, and he has the idea that during a total eclipse of the sun, you could measure the bending of the path of light. And the logic goes like this. The moon completely occults the sun, helpfully occulting its blinding rays. And because it's occulted the blinding rays of the sun, you can try to image an object that is directly behind the sun. So imagine in this particular case, it was the Hyades star cluster, which was directly behind the sun. And it's the light from the star cluster ordinarily should fall right into the sun, and you would not be able to see it. There would be total eclipse, the moon would occult the sun, and you would not see the star cluster. But instead what happened is the light from the star cluster took this path around the sun, because space-time is curved around the sun, and the light was able to fall freely along that curve in space-time. And so to you, the observer, or in this case, Eddington and his telescopes, it would look to you like the system had been deflected and was arriving from a different direction. That was the theory. If they measured that deflection, as predicted by Einstein's theory, they would have confirmed the general theory of relativity. Now, they have to travel, the eclipse is only in totality in a swatch of the Earth that covers this island off of Africa, Principe, which is where he led his team to observe the eclipse, and also covers part of Brazil, where he had a second team observing the eclipse. And there they are with their telescopes, and it's raining. They're under cloud cover, and they're worried they're not going to be able to make their observation. This would be the second time after this disaster in the Soviet Union, where they retained his equipment and threw him out. And it would be the second time many years later. There aren't that many total eclipses to rely on to do this observation, but the clouds break a little bit into the eclipse. It only lasts for about 7 minutes totality. And they are able to collect the data. Now, there's some historical argument about the accuracy of the data and interpretations, but the gist is they come back and they say, indeed, they have measured the bending of the path of light due to the curved space-time around the sun, exactly as predicted by relativity. And I think there is an important historical point to make, which is this is 6 months after the end of World War I, and Europe is devastated. And Einstein, being a citizen of Germany, is considered an enemy. Here are these two countries that were fought bitterly and are suffering terribly in the aftermath of the war. And Eddington, being this pacifist, really drives this sort of path towards science. And I liken it to stepping out of the shadow of the war into the shadow of the moon. And they realize that they're citizens of the same Earth, and there's this huge celebration. It really catapults Einstein's fame. Einstein, his reputation in the English-speaking world begins at that moment. And Eddington becomes the kind of harbinger and the translator for relativity. And it's a beautiful story. So it was only 1919, May 29th, I believe. And there's a beautiful story we'll get to that happens on the centenary of that expedition. Now, there are all kinds of curves in space-time. I mean, I can take a rock and it will fall in a straight line. That doesn't mean space-time isn't curved. That's just one simple path. I can throw something and it falls in an arc. Light will travel in a bent path. If I throw something fast enough, like the International Space Station, which is traveling, I know you don't do kilometers, I'm sorry I didn't translate for you, I usually do kilometers, but it's over 17,000 miles an hour. Very fast, the space station is cruising. And if I throw it fast enough, it can execute a full circle around the Earth. Now, the International Space Station, it's important to emphasize, has its engines cut off. It is not firing its engines to maintain course. It's not like driving a car. Once they get into the orbit that they want to be at, once they're traveling fast enough so that as they fall, they always clear the horizon, they never fall into the crust of the Earth, they turn their engines off. The International Space Station is in complete free fall. I know we look at the astronauts and it looks like they're floating, and we think, oh, they're floating because they're so far from the Earth that they're not feeling the gravitational effects. That's not true. They're not that high up at all. They are definitely feeling the gravitational effects of the Earth. It's just that they're falling on a perfect path that they always clear the horizon and they continue to fall. And that circular orbit is a measure of the curved space-time around the Earth. It is tracing one of the curved paths around the Earth. Another path would be to launch a spacecraft directly off the Earth and to launch it fast enough that it actually escapes, it genuinely escapes the gravitational pull of the Earth. And we do this all the time when we launch spacecraft. That's exactly what we're aiming to do. We're going to send them to Jupiter, we're going to send them out of the solar system, and the whole trick is to send it fast enough that it's not pulled back down. So what comes up does not necessarily come down. And that leads us to the black hole. So 6 months after Einstein publishes his general theory of relativity, a friend of him writes a letter, a beautiful, elegant letter, Karl Schwarzschild, who's writing to him from the Russian front. He had enlisted in the German infantry as a soldier, even though he was a 40-something-year-old accomplished astronomer. And he writes to Einstein, as you see, the war has treated me kindly enough, and I've had the opportunity to wander through the land of your ideas. And he sends Einstein a mathematical solution to Einstein's theory, which posits the following thought experiment. It's just an imagining. Schwarzschild says, imagine I took all the mass of a star and I crushed it to a point. He doesn't presume to know how to do that. He doesn't presume to explain if nature would allow such a thing to happen. He just says, imagine it. And in the process, he describes the shape of space and time around this object crushed to a point. Now, it does not earn the name black hole for many, many decades. Einstein's fascinated by this mathematical solution. He helps get it published. Unfortunately, Schwarzschild dies from an infection contracted on the Russian front within a year. And he never lives to see the implications of his solution. Now, many decades later, Einstein thinks, so this is, at the time, Einstein thinks, oh, this is lovely, this is very elegant, this is mathematical, but how are you going to crush matter to a point? That's absurd. Nature will not allow it. And he says, nature will protect us from their formation. It takes decades for many influential scientists, including Oppenheimer, who was working on the bomb project for World War II. And the same nuclear physics that goes into understanding thermonuclear explosions in a bomb goes into understanding thermonuclear explosions in a star. Turns out to be the same physics. And they begin to realize that that is an incredibly powerful source of energy. It keeps stars bright and aloft and illuminated, but eventually even stars are going to run out of thermonuclear fuel. They're going to run out of atoms and elements to fuse, to release this energy that keeps them bright. And when they do, they will not have enough resistance to unmitigated collapse if they're heavy enough. And Oppenheimer publishes this paper in 1939 with a student of his. It's the same day that the Nazis advance on Poland. And so this paper falls into obscurity. It is not exactly front page news, but the paper essentially says, we do believe that nature will not protect us from their formation, that nature has thought of a way to make black holes, still didn't have the name in 1939, that when the thermonuclear fuel runs out, if the star is heavy enough, it will begin to collapse under its own weight, and there will be no resistance to the catastrophic gravitational collapse. There is a famous American relativist, John Archibald Wheeler, who took this charge up, did not believe Oppenheimer's results, began to argue with him, but took up the charge of understanding this. And it was in 1967. So this is 50 years after Einstein received that letter from the Russian front, from his friend. Oppenheimer, with the sophistication of the multiple bomb projects by then, and understanding the nuclear physics, concludes that in fact, black holes will be formed in nature. And he's the one who coins the name. He's tired in this lecture of saying the end state of catastrophic gravitational collapse, a mouthful which he has had to say multiple times in this lecture, which apparently, rumor has it, happened down the street from where I'm standing. I'm at Columbia University right now in New York City. And apparently this happened 6 blocks away. He was at a scientific center near Columbia giving this lecture. And somebody allegedly shouts from the back of the room, "How about black holes?" And Wheeler latches onto it and he writes in this paper, the star, like the Cheshire cat, fades from view, leaving behind only its gravitational attraction. And he calls it a black hole. And so that's when the term was coined, and it's stuck with us ever since. And so here's an image of a black hole. It's a very interesting concept because what you're really looking at is in this painting, which is very accurate in some sense of what happens when we try to look for a black hole, is all you can see is the bright stuff around it. Technically, the black hole is actually empty. So let's talk about that for a second.